times C. So 2 times 5, that's 10. Okay, so 6 plus 10, 16. So that works. So the rule holds for that particular case. But okay, now let's do the dual. So now this would be the plus here, okay, and that'd be the times. Now, so is A plus B plus times C the same thing as this question mark? Right? Now, we have to find one counterexample where this is not equal to that, and that means the arithmetic equivalent of this dual is not true. Right? So let's actually do it. So let's calculate what the left-hand side is for these three values. So you know, 2 plus B by C. What's that? 3 by 5, 15. So 2 plus 15 is 17. Okay, so that's 17. Now the right-hand side. So the equivalent of this dual in arithmetic. So that'd be A plus B, isn't it? Times A plus C here. Okay, I'll plug in the values. So A plus B, that's 5 times A plus C. A plus C, so that's 7. Okay, so you get 5 times 7, that's 35. But 35 is not equal to 17. Right? So this and this are not the same. It fails. Okay, so don't. Well, yeah. Let's just toss it in for interest. So this distributive rule for Boolean variables works both ways. This is sort of the dual of that one. This one's the dual of that one. When you're just swapping around the ors and the ands signs. Okay. All right. Now a whole new topic. Oh, hold on. Yeah. In the textbook, there's a whole page that gives you a list of technical terms, definitions, that we have done up to this point. We're now on page 16, it's on the left hand side, page 16 of the text, this left side. Okay, and what you see there is a whole list of mathematical terms, technical terms, and on the left there's a column are the technical terms, the labels, the names if you like, and on the right column are the corresponding definitions. Now I'm not going to read out the whole thing. If you've got the textbook, check them for yourselves. But what I will do is I'll read out the technical term, and I'll pause a little bit between each term. And now you can stop. Now you've got a video, right? You can stop it at any time. So I'll read out a term, and I suggest then you stop, and then give a definition of that term. And if you're hesitating, or if you can't, or you've forgotten, well then you know you need to do a bit more study. Okay? So here's the list. There's 20, 30 terms. We've done quite a few already. Okay? So I'm asking you to give a definition of each of the following terms. Okay? In this context, in theory of computation. Alphabet, argument, binary relation, Boolean operation, Boolean value, Cartesian product, complement, concatenation, conjunction, connected graph, cycle, directed graph, disjunction, domain, edge, element, empty set, empty string, equivalence relation, function, graph, intersection, k-tuple, language, member, node, pair, path, predicate, property, range, relation, sequence, set, simple path, string, symbol, tree, union, vertex. Okay, so test just that's a sort of a quiz, if you like. So test yourself to see if you know the definitions of all those terms. And if you don't, if you failed on some, we'll go back and revise. Right? Okay, so next topic, a new section. The 0 here refers to the chapter number, chapter 0, and this is the section number. So we're into a whole new section now. So you know, a new big topic, and the topic is definitions. What are definitions? And theorems, very important concept in pure mathematics, and proofs. Okay, so I have lots of pure mathematics books, and believe me, they're just full of theorems and proofs. Like you have a theorem statement, you know, some mathematical statement. So it'll be theorem 3.5, you know, just to label the theorem. And sometimes it'll be given a name, like Artin's theorem or Joe Schmo's theorem. And then followed by the statement of the theorem. It's just some mathematical statement. Some mathematical object has such and such a property, for example. And then following that is usually the word proof, you know, colon. And then there's a mathematical proof that the statement in the theorem is true. And in fact, a theorem is a mathematical statement that has been proved. That's what a theorem is. And what's a proof? Well, that's what we're going to be talking about this in the next session. Okay. So there's sort of these three things that are fundamental to pure mathematics, and you may ask, well, this is a computer course, isn't it? Well, it's the theory of computation, and it's in a sense a branch of mathematics. There's a lot of theorem proving, pure mathematical type thinking involved in theory of computation. It's the most of all the subjects in computer science. Theory of computation, you know, complexity theory, stuff like that, is the most mathematical, right? And therefore a lot of people think it's the hardest, the most abstract. So if your brain has trouble with the abstractions of pure mathematics, pure mathematical reasoning, you know, proving things, then you may find this subject, this course, somewhat difficult. All right. So statement here: you know, theorems and proofs. They're the core of mathematics. In the textbook, he uses the term the heart and soul, you know, the very nature of what pure mathematics is about. Okay. And what are definitions? Well, I've been using like the 3 bars for definitions a lot. You need to define your terms. You need to give a meaning to the symbols that you're using. So typically a definition would take the form of some symbols on the left-hand side, and then 3 bars, you know, which is the definition sign, and then some statement on some expression on the right-hand side. And you interpret that whatever is on the left-hand side is given the meaning is defined as whatever is on the right hand side. So the right hand side is the definition of the left hand side. So typically you would introduce some new concept, some new name, and you'd put that on the left hand side, and then 3 bars, meaning is defined by, and then what's on the right hand side is your definition, the meaning that you give to the symbol, name or whatever on the left hand side. Okay, so definitions, they describe what it is that you're talking about in mathematics. It's rather vague. The so-called objects, the mathematical things that you're manipulating and making deductions about, and it's sort of hard to pin this down. So various ideas and concepts, notions, as Sipser calls them, and well, getting into the next session, but well, you probably see this first line. A definition can be quite simple. For example, well, the definition we use, I'm sure Sir Bertrand Russell will probably not agree, but the concept, the notion of the idea of a set, we defined fairly simply and easily. We just said it's a bunch of things, a collection of things that you label as a unit. And some definitions will be very complex, like the very notion, the idea of security. Oh, I don't know if you can see the second line. The idea of security in the context of a cryptographic system, secret writing, right? Encrypting, converting, translating an ordinary message into some secret code, right? And then transmitting it, and then doing the opposite at the other end, like decrypting, untranslating it, translating it back to the original message. Okay. Now, whether such a system is secure, well, you'd have a hard time defining what that means. Okay, so that would be an example of a complex definition. All right, so just continue on with the next session.